All right. Good afternoon, everybody, or whichever time it happens to be where you are. There seems to be a fair number of you here today, which makes me very glad. And while the numbers are seemingly still growing, I think it's a good time to slowly get started with today's webinar. Today's speaker is Jere Mäkinen, who did his PhD in Aalto at the same time with me, and then went to Yale to work on atomic BECs or atomic gases, and now is back in Finland. Today he will be talking about quantum turbulence and the Kelvin-wave cascade. Jere, please, the stage is yours.
Okay, thank you. Well, first of all, thank you, Samuli, for inviting me here, and thanks to the other organizers for letting him. Yeah, I also like to thank about all these people mentioned in the first slide for all their contributions in various aspects of this study. By the end of the talk, I hope I have managed to explain to you what I mean by rotating quantum wave turbulence, as well as why we believe that we do see the onset of the Kelvin-wave cascade in our experiments. So first off, some little background. So what is turbulence? Turbulence is often described as chaotic motion of fluid as opposed to orderly laminar flow. Transition to turbulence can usually be estimated using a dimensionless parameter called Reynolds number, which is defined as the ratio of inertial and viscous forces. Generally speaking, the Reynolds for a low Reynolds number, the flow tends to be laminar, while for a high Reynolds number, the flow tends to be turbulent. Note this is not always true though. So there are some cases, for instance, in the pipe flow, where in the large Reynolds number limit, you still may have a laminar flow, but the tendency for chaotic behavior increases. So even for a very small perturbation, your flow would go immediately turbulent in that case. Also, one central aspect of the turbulence is that there is a cascade of energy from the highest length scales towards the lowest length scales, while most energy is usually contained at the largest length scales. There's a thing usually referred as to the zeroth law of turbulence, which says that dissipation in this picture, dissipation would remain finite even in the limit of zero viscosity, or equivalently, well, infinite Reynolds number. Okay, so what do I mean by rotating turbulence? What is meant by rotating turbulence? So in addition to the Reynolds number, the flow can be characterized by the Rossby number, which is another dimensionless parameter that is defined as the ratio of inertial forces to the Coriolis force. So from this definition, one can immediately see that in the limit of low Rossby number, rotational effects are important, while in the opposite limits, they can be neglected. From this, one can deduce that the rotating turbulence means a case where Rossby number is small and Reynolds number is high. Such a turbulence is relevant for fluid motion on planetary scales, for large-scale turbomachinery, as well as rotating superfluids, among other things. There are a few different frameworks, theoretical frameworks one can use to describe rotating turbulence. One of them is the 2D turbulence, due to the orientational effect of the rotation. So you would have essentially two-dimensional flow in the limit of high rotation velocities. Another one that has been suggested and even observed recently is the ensemble of three-dimensional inertial waves. And which regime your turbulence falls into depends on the parameters, on the experimental parameters, such as the rotation velocity or the height of your fluid element. In our experience, we are in the three-dimensional inertial wave regime. Okay, so as an example about rotating wave turbulence, there is that means that this Rossby number is small and the Reynolds number is high, which means that there are strong rotational effects which are driven by nonlinear wave interactions So as I mentioned in the previous slide, this entire flow field has been suggested to be describable by an ensemble of inertial waves. And there's this nice picture about the study on classical fluids where as a function of decreasing Rossby number, so these are the lowest Rossby numbers and they're increasing as in this direction. This is the highest Rossby number. As you can see, the energy contained in the flow field gets more and more concentrated on the inertial wave dispersion relation. As you can see by the highlighted color here, inertial waves have a very, very distinct dispersion relation. They essentially are limited to below twice the rotation velocity. Okay, so what is meant by rotating quantum wave turbulence is essentially the same thing as in the previous slide, but now you have a quantum fluid or superfluid where the vortice is quantized. There are some differences to classical turbulence, however. So in superfluids, the transition to turbulence is governed by, instead of the classical Reynolds number, which contains viscosity, in helium-3, 3p, it has been found that it can be, transition to turbulence can be characterized by dimensionless superfluid Reynolds number, which depends on the mutual friction parameters alpha prime and alpha. And this has been shown to work quite well in helium-3b. In helium-4, people may have some other definitions where you replace the viscosity by the quantum of circulations. Now, one could immediately ask the question, are inertial waves supported for quantized vorticity or when the vortice is quantized? So let us try to answer that question by starting to look at some wave spectrum. So in this paper by Henderson et al., they derived the general vortex wave spectrum for all cases in rotating superfluid, but the axially symmetric modes have a dispersion relation that looks like this. So if we fix the radial wave number and plot this thing as a function of the set directional wave vector, you get something like this. Right, so if we take the classical limit where the quantum of circulation vanishes, so essentially nu(s) goes to 0, you end up getting the inertial wave dispersion relation, which looks something like this. So indeed, it's limited to frequencies below 2 omega. So in superfluids, however, the predicted dispersion relation is like this. So what is the difference between these two? No one's surprised if you take the short wavelength limit where the set directional or the wave vector along the vortices, in this case, is much larger than the radial wave vector. You recover the dispersion relation for Kelvin waves. Okay, so what are inertial waves and Kelvin waves then? So inertial waves in superfluid, they are shown in this movie that they are essentially a collective motion of large number of vortices where they act in phase, creating a three-dimensional large-scale flow field. So in a sense that they were observed in the classical fluids, that have been observed in the classical fluids, I don't know of any direct observation in the superfluids to date. However, there are some measurements where inertial wave resonances have been shown to help in generating turbulence in a cubic container, for instance. So they should exist also in the superfluid sample. Now, Kelvin waves, on the other hand, are excitations on individual vortices, so they are in the short wavelength limit. And they have these weakly structures they are helical excitations on a single vortex. And a cascade of Kelvin waves has a crucial role in quantum turbulence in the zero temperature limit, since they are the only thing that is predicted to transfer energy to low enough length scales such that dissipation could take place. Now, theoreticians have been arguing about how does the energy scale with the wave vector in the Kelvin wave cascade. And individual Kelvin waves have been observed in a very nice way by reconnecting two vortices and you see the creation of Kelvin waves in this reconnection process. But to date, there is no observation about the cascade. Okay, so this is roughly how our experimental setup looks like, or what is the experimental setup. So we have a quartz glass container that is filled with helium-3b. We have treated the inner surfaces with hydrofluoric acid to make them as smooth as possible to avoid any vortex spinning in the inner surface of the glass cell. So we extract information about vortices by using nuclear magnetic resonance measurements. And you can see an example trace here. So we excite magnons, or magnetic quasiparticles, which form a BC and start precessing coherently with the same phase and frequency. And as time goes on, the magnon number decreases, this precession induces a voltage signal in the pickup coils, which we can then measure. As time goes on, the number of magnons decreases, which means that the signal induced in the pickup coils decreases, and they also change in frequency to some degree. In any case, the rate of this dissipation is a measure of vortex density, while the final frequency can be used to deduce, for instance, the vortex tilt angle with respect to the axis of rotation. In addition, we have some devices called quartz tuning forks, which are located here in the bottom of this sample. And they are mechanical resonators that are sensitive to the thermal excitation density, and they are used to deduce the temperature in the system. All right, so the actual temperatures in the system are we are working on in the zero temperature limit, essentially between 0.13 and 0.2 TC. We have made measurements in more or less the whole accessible pressure range for the liquids, meaning 0 to 30 bars. And we are working roughly at rotation velocities below 2 radians per second and using this kind of angular accelerations. All right, so this is the experiment we are talking about here. So we start with by preparing an array of rectilinear vortices by rotating the sample at a constant angular velocity. At some point, we start modulating the rotation velocity, which creates waves on these vortices. We keep on doing that until we have a steady wave turbulent state. At some later point, we stop the modulation to some rotation velocity, and we observe how this vortex state decays. So I will tell you in a bit why, but indeed the vortices couple to the drive mostly via the surface at the bottom, where there is a heat exchanger volume, where the surfaces are by design rough. And in this kind of system, you have a high vortex polarization due to the rotation. And that also is known to reduce the reconnection rate in the turbulent state. Okay, so let's take a look at what happens when we start modulating the rotation velocity. So first of all, our drive is at very low frequency, which means that the wave vectors are going to be large, and this lies in the inertial wave regime, so in the classical regime, if you like. And the signal looks like this. So we have two spectrometers, as I mentioned. They're separated by some 9 centimeters. And what we observe is that we see the lower spectrometer react first, and then the upper spectrometer a bit later, which means that there is some sort of a vortex polarization from that propagates from bottom to top. So starting from the center volume. And we see a few things in this picture. So if we compare the propagation velocity of this vortex front extracted from the initial response when this changes from the steady state value, extracted from propagation velocity from that information, we see that it nicely agrees with the inertial wave phase velocity. Then on the other hand, if you look at the upper spectrometer, which is further away from the rough surface, and we take the turbulence build-up time roughly between the time when it reaches the steady state here, and that of the initial response, we see that it's roughly about 100 seconds. And this agrees with our estimate for the inertial wave or development time of the inertial wave turbulence, which we estimate to be something like 80 seconds. Also, we see no change in the NMR relaxation rate during this time, which suggests that the vortex density remains constant during this time. Okay, so I think it's a good time to talk a little bit about the model of pumping. So what's going on at the center volume? So assume that the vortices are pinned to the center volume, and then you start applying a drive with omega. This characterizes the angular velocity of the vortices or the superfluid flow field. In this case, vortices should experience a force that is the sum of the Magnus force and that of mutual friction. Right, so there is a paper that suggests that if this force is large enough, namely larger than this value, which is called the vortex tension, the force magnitude is in fact limited to the vortex tension. You cannot apply a force larger than this. Now, we estimate that this is true for, in the low temperature limit, this is true for, let's say, in 1 millimeter radius, when the difference between the rotation velocity of the container and that of the superfluid is something like 3 × 10⁻⁴ radians per second. The typical amplitudes we use for excitation are like 10⁻⁻1 radian per second. So these are orders of magnitude smaller than any realistic changes in the angular velocity. So we are essentially always in this regime where each vortex is acted with the constant force. Now, if we allow, in this picture, we do allow this to be non-perfect. So we allow there to be a fitting parameter beta, which characterizes the efficiency of this pumping. Okay, another prediction from this model is that for a step change, where you change the drive between some values, the superfluid velocity reaches the final angular velocity approximately linearly in finite time, which has this value. Right, and we can also calculate the average power during the pumping. Okay, so this kind of behavior is unique to quantum fluids or superfluids, as the vortices are partially slipping. So there is no slip boundary conditions. Also, there is no friction in a sense that it's not proportional to the velocity difference between the superfluid and that of the container. So this is a unique kind of boundary layer interaction for superfluids. All right, then let me say a few words about how we interpret the NMR signal that we saw. You saw that the frequency was decreasing when we started modulations. So we have performed some textural calculations with using uniform vortex tilt. So there is a density of vortices and they are just tilted uniformly along the axis or with respect to the axis of rotation. And we use some experimental input to characterize what is the effect of a single vortex there, using measured energy levels in this Magnum condensate. And we found that the resulting frequency is approximately proportional to, or linearly proportional to sine squared of the tilt angle of these vortices. Here's one example you can see. So this dashed line is the approximate relation written here, while the red one is the actual simulation. Now we have measured this or estimate this in a few different pressures, and it looks like this effect. So this frequency shift here with respect to the tilt angle of the vortices scales with the vortex core size. All right, so let's take a look at how the data looks when we stop the modulation. So first of all, if we convert this to the vortex tilt angle, one can immediately see that this value during the steady state is reasonably large. So this corresponds to something like 55 degrees, if I remember correctly. in the average tilt angle of the vortices. So this is not like a linear tilt in each vortex, but it's rather a tilt caused by something like Kelvin waves. Another characteristic feature of this signal is that it has a two-stage decay process. So you see that we stop the modulations here, and there is quite some time where essentially nothing happens. So the polarization remains at a similar level as during the modulation. So during this first stage, the vortex polarization remains roughly constant. And we estimate that this comes from the decay of global flow. We'll talk more about that in a bit. In the second stage is essentially exponential relaxation that we assume comes from relaxation of this tilt angle that is mainly caused by Kelvin waves. Okay, so in these experiments, we have plenty of parameter space to explore. We can change, for instance, pressure, which, for instance, changes the vortex core size, among other things. We can change the temperature, which changes the absolute value of the mutual friction parameters. We can change the angular velocity, which changes the vortex density, or we can change the amplitude of modulation. We could change the final rotation velocity to a different place to control the amount of kinetic energy released in this process. There's a kinetic energy release between the average velocity and the final velocity if they're not equal because of the vortices imitate the solid body rotation. We can in principle also control the excitation frequency to excite different wave modes. So given all this, what can we learn about this system? Okay, so let's start looking at the first decay stage. So as I mentioned, the assumption here is that there is a decay of global flow via quantum boundary layer, which also means that omega, the superfluid velocity, reaches the final angular velocity approximately linear in time, or it reaches exactly in this time. So we can test that hypothesis by studying the dependence on the omega naught minus omega f, so the mean angular velocity minus the final angular velocity. And you can see that the blue points are our experimental data, while the black curve is a fit to this equation. So we can see that it's a really good match, right? So this seems to be coincide with our expectation. Okay, so next we can test how it depends on temperature. So how it depends on the value of the mutual friction parameters. So if you look at this equation, in principle, you don't know what this fitting parameter beta, which is approximately 1 here, is doing. But none of the other parameters should in principle depend on temperature. And indeed, if we change the temperature, the mutual friction parameter changes almost by 2 orders of magnitude in this range, but there's essentially no difference in this time scale. Okay, so this thing seems to be temperature independent, which also means that beta, or this fitting parameter beta, is temperature independent. So what else can we study? For instance, if we change the pressure, there is a change in the vortex core size, and that does seem to have a clear effect on how this timescale behaves, right? So for higher pressures, it seems to be a faster timescale, while for lower pressure, where the vortex core size is bigger, the timescale is much longer. All right, so if you plot the value of the fitting parameter beta, which is essentially the slope here, as a function of pressure, and we again compare that with the vortex core size, this is 1 over this beta, we see that it really nicely also matches with how the vortex core size behaves as a function of pressure. So while we don't know this for sure, it seems to indicate that this spinning, or whatever this efficiency of pumping, gets higher with decreasing vortex core size. So maybe the vortices have been somehow stronger for smaller vortex core size. Okay, so how about, for instance, taking the frequency of excitation. So fixing the final angular velocity and the amplitude by just changing the frequency, we see that this length scale gets actually bigger in presence of inertial wave resonances. So this seems to also suggest that there is some energy accumulation in the presence of vicinity of inertial wave resonances for this container. All right, so let's now concentrate on the second relaxation state, which is the exponential relaxation. So our assumption is that it's a decay of Kelvin waves via mutual friction, right? So for a monochromatic Kelvin wave, the dissipation should be exponential with a times constant essentially defined by the wave vector of this Kelvin wave. Now, one can also show that if you have a cascade of Kelvin waves between some starting wave vector and some final wave vector, you essentially end up getting the same result, but with this k alpha replaced by k star to 1/3 power times kn to the 2/3 power. Okay, so essentially this decay process look the same. So how do we tell the two apart? So first question that comes to mind is, what defines this k alpha? So there is a one clear length scale in the rotating case, which is the intervortex distance. It just depends on the angular velocity of the superfluid. So if we plot this inverse of this time constant as a function of rotation velocity, final rotation velocity, which is essentially vortex density, we see that it's indeed a linear dependence that seems to even go through zero for zero angular velocity. Okay, so that indicates that this k alpha is indeed proportional to the intervortex distance, or 1 over intervortex distance. Now the next question would be, what is the dependence on temperature? So let's say this guy is defined by intervortex distance. Let's say this guy is fixed. It should still depend on alpha, right? So indeed, when we perform these measurements at the different temperatures, and we see that the dissipation rate does increase with increasing temperature, which is in line with what you would expect from this alpha dependence over here. Okay, so what else? So yeah, this is if we plot the slope here, which is essentially the rotation velocity normalized dissipation rate as a function of the mutual friction parameter alpha. This is what we get. Okay, so can we make sense of this measurement? Right, so the starting point is that we have this known decay for Kelvin waves, and that this k alpha, which defines this time scale, depends on essentially square root of omega. It depends on the inverse intervortex distance. So that means that the rotation velocity normalized relaxation rate depends linearly on alpha, or should depend linearly on alpha. Okay, so let's plot that line here. So as you can see, this linear dependence is not really a good description of what's going on here, which indicates that there's no other way than that k alpha is a function of temperature. So at this point, we know that this length scale is not fixed as a function of temperature. So it's not fixed by intervortex distance, but it actually does also depend on temperature. And this is indeed what is expected for Kelvin cascade, since as the temperature goes towards the zero temperature limit, the cascade should expand towards higher wave vectors. All right, so what else can we learn from here? So if we take this value here, which seems to be a good fit for the higher temperature data, and then we use some estimate for the end wave vector for the Kelvin wave cascade from this reference, we can deduce that this rotation velocity or vortex density normalized dissipation rate has this form. So it's some number which is constant times effective kinematic viscosity over kappa to the power of 2/3. So why I want to write it this way is this is typically used, at least in turbulence describing helium-4, to characterize the energy dissipation rate in quantum turbulence. Moreover, if you take these assumptions, you find out that this dissipation rate should be independent of alpha, so independent of temperature, which is the superfluid equivalent of the zeroth law of turbulence. And by plotting or extracting the value from these measurements, we estimate that this effective kinematic viscosity in our case is something like 10 to the -6 kappa. So this is an extremely low number as a reference for counterflow turbulence, which is known to be homogeneous and isotropic turbulence. This effective kinematic viscosity is something like 10 to the -1 kappa, while this effective kinematic viscosity is known to be smaller for cases where the vortices are polarized, like here, or when there are no reconnections, which is also what we suggest is going on here. So far, the smallest value I could find in the literature is something like 10 to the -4, which is still a few orders of magnitude higher than we estimate for these measurements. Okay, so lastly, for these topics, we know now we have a good reason to believe that we know that this case start is fixed to roughly the intervortex distance from the high temperature fit, and then we have some estimate for this. We can calculate this as a function of temperature from the data that I just showed you. So we can estimate the extent of the Kelvin-wave cascade in units of k end over k start, and this is what you get. So if you compare our experimental data, or what is these values that are extracted from our experimental data with numerical simulations from this paper, you find that they are actually reasonably similar as a function of alpha. You also note that the Kelvin-wave cascade, even at the lowest temperatures, only extends about an order of magnitude in the wave vector space. So this is sort of a measure of the onset of the Kelvin-wave cascade. Okay, so now the fair question is that what could be the role of vortex reconnections in this picture? So as I mentioned, we performed some vortex filament simulation by modulating the omega in the same way as in the experiments. And it's noteworthy that the small scale structures in those simulations appear before the first reconnection. Also, at later times, the reconnection rates remain fairly small. In those simulations, it's something like 1 reconnection per vortex every 20 seconds or so, which seems very low to run a cascade. Also, both simulations and experiments on spin down show mostly laminar decay for helium-3b. Here you can see an example from those simulations where you indeed do get some reconnections, but they are first of all concentrated really close to the boundaries of the container, and the overall behavior is still laminar. I should also mention that the magnum condensate, which we use to plot the vortices, is located close to the middle of this container, so it should be insensitive to anything that's going on close to the boundaries nonetheless. On top of that, this high polarization in the experiments and the low value of new prime extracted also suggest that the reconnection rate should be very low. So we believe that the role of vortex reconnections in these kind of measurements can be ignored. So just to recapitulate what I've been talking to you about is essentially this phenomenological model. So the whole thing is that we are driving energy into the system via quantum boundary layer by modulating those angular velocity, which then excites some inertial waves. And there is a cascade from inertial waves to the Kelvin waves. And finally, they are dissipated via mutual or through mutual friction. We can also write this equation or phenomenological model into equations, which are shown here. So essentially, this is the quantum boundary layer for superfluid velocity. Then there's the inertial wave cascade, which has the input from this pumping through the quantum boundary layer. Then it has some cascade. And in the Kelvin wave, energy in the Kelvin waves is essentially energy input from the inertial waves minus mutual friction dissipation. And then we can, in principle, use this phenomenological model to simulate what's going on with realistic drive and using some experimental input for these parameters. Right, so this is how results of this numerical simulation would look like. So when we start the modulation, the mean angular velocity doesn't really change, but when we do stop the modulations, it goes linearly to the final value, right? If you look at the energies, you see that the inertial wave, energy in the inertial waves, which is the blue line, saturates much faster than that in the Kelvin waves. And this, in fact, this timescale coincides with the experimental one for saturation of the NMR signal. While the saturation in the Kelvin wave, the energy takes much longer. We also see that both of these start decaying essentially immediately as you ramp down the angular velocity to the final value. Right. We can also use these energies or calculate energies to convert that to the vortex tilt angle. This is what we get. So the difference between the black line and the red line is that the black line only contains contribution from Kelvin waves, and the red dashed line contains contribution from Kelvin waves and inertial waves. As you can see, this is clearly dominated by Kelvin waves alone. Right. So as for the decay, you can see that initially there is a two-stage decay. So this initial part, the vortex tilt angle, is really not changing from the value in the steady state until this rotation velocity has reached the final value, or the superfluid angular velocity has reached the final value, at which point it starts to decay roughly exponentially. And if you compare that with the tilt angle extracted from the experiments, you see that the magnitude is reasonably similar, as well as the length scales. Right. So in more detail, what do the simulations tell us? They are in agreement with the inertial wave development time, experimental one. They also show a clear two-stage decay, as in the experiments. The steady-state tilt angle is in good agreement also with the experiments, as are the decay timescales. Now, what is not in agreement is the tilt angle from inertial waves. Also, this simulation suggests that if you would stop in the middle, or if you would stop the modulations in the middle of mean angular velocity, you would see no two-stage decay, but essentially a single-stage decay, which is not true in the experiments. So there is some extra energy contribution that we are not considering in this phenomenological model that does exist, for instance, in the presence of inertial wave resonances in the experiments. Additionally, we have a qualitative agreement with the development time of the Kelvin-wave cascade, which I can talk to you about if you're interested, and the saturation of the sign of the vortex tilt angle for increasing as a function of increasing drive amplitude. Which brings me to my conclusions. So in these experiments, from the independence of the early decay, we deduce that this is indeed coincides with the quantum boundary layer picture of that I mentioned earlier in this talk. From the build-up time plus resonances, we deduce that we have some inertial waves in the system. Well, are these identical to those in classical fluids? That I don't know, but we do see some effects in the vicinity of inertial resonances, plus the propagation velocities coincide with what you would expect for them. From the exponential decay plus the final angular velocity dependence, we see that this dissipation length scale is fixed by the intervortex distance. From the temperature dependence of this exponential decay, we believe that we do see the onset of the Kelvin-wave cascade. Okay, then from simulations plus previous works from spin down, plus the fact that we see extract an extremely low value for the effective kinematic viscosity, we believe that we are indeed we see wave-driven turbulence and not reconnection-driven turbulence in this case. Finally, we have qualitative and semi-quantitative agreement between simulations and experiments. That's all I want to say. Thank you.
Thank you, Jere, very much for a very interesting presentation. Are there any questions? Please put your hand up if you want to ask a question.
Well, I see Carlos' question, and this is something like what 0.1 millimeters is the average distance between vortices in this case?
Yes, thanks. Well, while we wait for questions, you alluded to the possibility of the realization that something may be missing from the numerical model. Could you speculate a little bit on what that might be?
Well, it doesn't take any geometry into account, so in principle you don't have any like inertial wave resonances, etc. So it's just pumping that that goes into the system, but there's no like energy storage, if you like.
Yeah, I see.
It's also, well, it's a finite sized system, so whenever you do something at the bottom, it takes time for the effects to propagate to the top. So that's also something that is in principle missing. It's just an average energy kind of calculation.
I am not currently seeing any questions here. Is there something in the chat? Apparently not. Well, I will give the people another short while to think about if they want to ask something, and use this gap to say that the next talk will be in 2 weeks' time, and it will be about room temperature Magnus-Bose-Einstein condensates in a solid state system. Details will follow by email. Well, if there are no further questions, then I will thank Jere for a fascinating presentation, and I will see you all in 2 weeks' time.
Okay, thank you.